probably seen how you can use Pythagoras' theorem to work out the sines and cosines of some rather useful angles. For example, you can work out the sine and cosine of pi by 6 using this standard triangle. The sine of pi by 6 is the opposite over the hypotenuse. It's a half. And this triangle, right-angled triangle with two equal sides, is very useful for working out things about pi by 4. Sine of pi by 4, opposite over hypotenuse, is just 1 over root 2. But supposing you wanted to work out a rather non-standard angle, like the sum of these two, pi by 4 plus pi by 6. What's the sine of that angle? Well, if I put these two together, then this is the angle I'm interested in, and I need to look at this triangle. Now, I know what that length is. I had that one before. That's just root 2. But I don't know what these lengths are. It's certainly not a standard triangle. I suppose I could draw the thing accurately to scale and get an estimate for sine of pi by 6 plus pi by 4, but what I'd really like is an accurate answer, or at least an answer that involves square roots. Now, believe it or not, the answer you get is that. And what we're going to do is show you how to get that. Now, you certainly wouldn't get that by measurement. The way you do get it is to use a formula. You use this formula, which tells you what the sine of the sum of two angles is in terms of the angles of sines and cosines of the angles themselves. Sine alpha plus beta is cos of alpha times sine of beta plus sine of alpha times cos of beta. What we're going to do in this program is to show you how to obtain that formula, and the way we're going to do it is to use some of the ideas of rotations that we've seen in Unit 3. But what have rotations got to do with angles? Well, angles aren't just things that sit in triangles. If you look at this one, you can regard this angle as an angle of rotation through pi by 6 plus pi by 4, or rotation through pi by 6 and then through pi by 4. Either way, this distance is the vertical distance that this point has moved under the rotation. So movement of points under rotations is going to be the key to getting our formula. Now, our formula is something written down. So obviously we've got to be able to write down information about the movement. Now, writing down things about points suggests that we use coordinates. For example, here, if this were an x-axis, then this distance would just be a y-coordinate. So what we've got to do is to find the effects of rotations on coordinates of points. And to get us started, here's Bob Margolis.
Well, rotations are only one of the 4 sorts of transformation that you've seen in this week's unit. And although what we want to find out about are rotations, I'll do a typical mathematician's trick and creep up on them from behind. I want to start with translations, because what I want to write down is easier for translations. Now, what do I mean by a translation? Well, something like this. Here's a shape, and here's a translation. The shape's moved bodily. In this case, the whole shape is moved bodily 2 units to the right. So how can we write this down? Well, let's look at what's happened. This point has moved to there. This point has moved to there, and so on. We'll write it down using an arrow like this. On this side of the arrow, we want to write down a symbol for any point, and on this side, we want to write down where that point goes to. Now, we know how to write down a symbol for any point. It's simply the coordinates. So the problem now is, what does a translation do to the coordinates of a point? This translation moves everything to the right by 3 units, and at the same time upwards by 1 unit. What happens to this point? Its coordinates are 1, 2. It moves across 3 and up 1. So its new coordinates are 4, 3. The same thing happens to other points. Along 3 and up 1. But the easiest way to remember how far to move is to look at the origin. Along 3 and up 1, it becomes 3, 1. Once we know what happens to 0, 0 under the translation, we know everything that there is to know about this particular translation. But what would we do if we wanted to know what happened to a general point? Well, first we need a symbol for it. I'm going to use UV. Now, this 3 tells us that the first coordinate, u, is increased by 3 to become u plus 3. And this 1 tells us that the second coordinate, v, is increased by 1 to become v plus 1. So uv goes to u plus 3, v plus 1, and we've got a symbolic form of the rule. We now know what happens to any point, because if we're given a point, all we have to do is to replace u and v here by its coordinates, and we know where it goes to. So now we've answered a question that we weren't asked about translations. Can we do the same thing for rotations? Can we write down a rotation in the form uv goes to something? Well, let's begin by looking at a simple rotation. This rotation moves everything round by a right angle, pi by 2. What happens to the point 0, 0 when we rotate? Nothing. It stays in the same place. It would for any rotation, so it doesn't tell us anything about this particular rotation. Let's try another point. 1, 0. This point certainly moves. It goes to the point 0, 1. So the first coordinate is reduced by 1 from 1 to 0, and the second coordinate is increased by 1 from 0 to 1. Now let's try this rule with another point. Will these coordinates be reduced by 1 and increased by 1? No, both the coordinates are reduced this time. Our rule doesn't work with this point. We need a rule that works for every point. Now we seem to have come to a dead halt. We wanted a rule so that we didn't have to write down what happened to each individual point. Everything about the rule should have been summarized symbolically. But the trouble with the rotation is that different points move by different amounts and in different directions. A point near the origin will move by a fairly small amount, like this. Whereas a point a lot farther away from the origin, like this one, will move a lot further and in a different direction. So changing the coordinates by a fixed amount won't work. If the changes will work for this point, they wouldn't work for this one. We'll have to change the coordinates by an amount which depends on what the coordinates were to start with and on the angle of rotation. So let's go a little more slowly. We've two things to worry about: angles and coordinates. When we looked at a special angle, pi by 2, it didn't seem to help us much. So now let's try looking at a general angle, alpha, but concentrating on a particular point. We'll concentrate on the point 1, 0 and rotate it through an angle alpha. This is the point, and this is the angle alpha. We'll call the new point x, y. What are x and y? The horizontal coordinate is x, and the vertical coordinate is y. But x and y are sides of a right-angled triangle, and we know the angle. It's alpha, the angle of rotation. How long is the hypotenuse? The hypotenuse came from here so its length must be 1. The adjacent side is just cos alpha, and the opposite side is sine alpha. So the coordinates of this point are cos alpha, sine alpha. But that's the point that 1, 0 goes to. So when we rotate through alpha, 1, 0 goes to cos alpha, sine alpha.
Before Bob goes on, let's just remind ourselves what we're after. If we rotate this point through some angle, then its coordinates become cos of that angle, sine of that angle. So if we rotated it through alpha plus beta, then its coordinates would become cos of alpha plus beta, sine of alpha plus beta. And this second coordinate, sine of alpha plus beta, is what we're after. I'm looking for a formula for that. But we can get to this point in 2 ways. Either like this, through a rotation through alpha plus beta, or by 2 rotations, first through an angle alpha, and then through an angle beta. Well, we know what happens if we rotate 1, 0 through an angle alpha. We've just seen that its coordinates become cos alpha, sine alpha. So what we've got to do now is to find out what happens to this point, cos alpha, sine alpha, when we rotate through an angle beta. But that's something we don't yet know how to do. That's the second part of our problem. All we know so far is what happens to the point 1, 0, not a general point like uv. So the next thing we've got to do is to see what happens to a general point uv when we rotate it. And the way we're going to do that is to exploit what we know already.
And this is what we know already. Here's uv, and we can imagine it as being at the corner of this rectangle, with sides u and v. Now what happens to this as I rotate it? The whole rectangle moves around. It's rigid, and if I knew what happened to this corner, u0, and this one, 0v, I'd know what happened to the rectangle, and so I'd know what happened to uv. Well, let's look at the corners. This one, u0, is on this axis and looks very like 1, 0, and we know what happens to 1, 0 when we rotate it. What about the other corner, 0v? Well, that's on the other axis, and if we knew what happened to, say, 0,1 when it's rotated, we ought to be able to work out what happens to 0v, and then we'd be able to work out what happened to uv. So let's work out what happens to the point 0,1 when it's rotated through an angle alpha. Here's 0,1. What are x and y this time? This is y, and this is x. So we work with this right-angled triangle. First, the hypotenuse. It comes from this distance, which is 1. This time, the vertical distance is the adjacent side, cos alpha. And the horizontal one is the opposite, sine alpha. So the first coordinate of the point is minus sine alpha. And the second coordinate is cos alpha. That's what we wanted. 0,1 goes to minus sine alpha, cos alpha. So now we know where both 1, 0 and 0,1 go when we rotate them. Let's use this to find the rule for uv. Rotate uv through alpha. It goes to x, y. What are x and y? Well, we'll start with y because it's easier. This vertical distance is y. We can't get it directly, but we can find it in two parts. This plus this. How can we find this lower distance? We can use this right-angled triangle just as we did when we rotated the special point 1, 0. The length of the hypotenuse is u, so the opposite side of the triangle is u times sine of alpha. Now for this upper distance. We haven't seen a triangle like this up in the air before, but it's exactly the same as this triangle down here. And this is like the one we used for finding the special point 0, 1. The length of the hypotenuse is v, and so the adjacent side is v times cos of alpha. The upper distance that we want is also v times cos of alpha. So the total vertical distance is just u times sine of alpha plus v times cos of alpha. Now for the horizontal distance. Can we split this up in some way? It's just this minus this. Again, we'll work out the lower distance first. Here's the triangle, and the adjacent side is u times cos of alpha. Now for the upper distance. Here's the triangle. It's the same as the other one. The opposite side is v times sine of alpha. This time, we have to subtract. We get u times cos of alpha minus v times sine of alpha. So now we've got the coordinates of the point. They're u times cos of alpha minus v times sine of alpha, u times sine of alpha plus v times cos of alpha. So that's where uv goes to when it rotates. And this is the rule that we want. It tells us where uv goes to when we rotate it through an angle alpha. Now let's use this to get the formula for sine of alpha plus beta.
Let's just remind ourselves of the strategy here. Remember, we take the point 1, 0, rotate it through an angle alpha to get to another point. We just call it uv for the time being. And then we rotate through the next angle, angle beta. And now we know that we've got this description for the coordinates of this point, where now we're rotating through an angle beta. But remember, I said that we'd compare what happens under those two rotations with what happens for the single rotation through the angle alpha plus beta. Well, we know that 1, 0 goes to cos of alpha plus beta, sine of alpha plus beta. Now we've got two descriptions of the same point. This description and that description. If they represent the same point, they must be the same. So the first coordinates must be the same, and these second coordinates must be the same. And it's these we're interested in. The second coordinate here is sine of alpha plus beta. That must be the same as the second coordinate here. And there's our formula. Sine of alpha plus beta equals this thing. All we've got to do is to replace u and v. Well, we know what u and v are. uv is what happens to 1 naught when we rotate through alpha. It just goes to cos of alpha, sine of alpha. So u is cos of alpha, v is sine of alpha. So now we're home and dried. All we've got to do is to go through this and replace everything by things we know. U we now know to be cos alpha. Sine beta we don't have to do anything about. Add v. Now v we've just seen is sine of alpha times cos of beta. And there's our formula. Sine of alpha plus beta is cos of alpha times sine of beta plus sine of alpha times cos of beta. So that's it. We've got our formula. Now I can use that to go and calculate sine of pi by 6 plus pi by 4, see if I get the same number that I showed you earlier in the program. Sine of pi by 6 plus pi by 4 is what we're trying to work out. It's cos of alpha, cos pi by 6, times sine of beta, sine of pi by 4, add sine of alpha, sine of pi by 6, cos of beta, cos of pi by 4. Now all these angles are standard angles. We can work those from standard triangles. Cos of pi by 6 is root 3 over 2. You can work this thing out for yourself afterwards. Sine of pi by 4 is 1 over root 2. Add sine of pi by 6 is a half. Cos of pi by 4 is the same as sine of pi by 4. Tidy it up a little bit, put it all over a common denominator, 2 root 2. We get root 3 plus 1. And that, if you remember, is exactly the number that we saw at the beginning of the program. So you see, this formula for sine of alpha plus beta is very useful for extending the range of sines and cosines that you can work out. But there are 1 or 2 other points I'd like to make. First of all, remember that we got this formula by comparing second coordinates after some rotations. Now, if you look at the first coordinates, you'll see sitting there just waiting for you to pick up a similar formula for cos of alpha plus beta. Again, it expresses cos of alpha plus beta in terms of sines and cosines of alpha and beta themselves. Now, the second point is that although this formula is very useful for calculation, it's also got a tremendous theoretical value. And you'll see just how important it is when you come to the calculus sections later in the course. And finally, there's a whole bunch of other trigonometric formulae rather similar to these. But don't be worried about them, because in a sense, the 2 that we've seen for sine of alpha plus beta and cos of alpha plus beta are the mother and father of them all, because you can get all these from the other 2 just by ordinary algebraic manipulation. Now, don't worry about those, because nobody would expect you to remember them. But I do think it's a good idea for you to have a shot at trying to work out 1 or 2 of them for yourself. And if you look at the text that goes with this program, you'll see that we've given you an idea how to get started on working out a couple of them. So, for the time being, goodbye.